Robots and robots. We are in the dawn of robotic uprising, or in an explosion of useful embodied intelligence. No matter how you see it, now is the right moment to get familiar with the humanoid robots. To understand why that is, it is best that we look back a little bit. Humanoids aren't new, and we didn't just figure out how to put motors into metal skeletons. Engineers have been building impressive prototypes since the 1970s, but most of the time they were just proof of concepts. It's always been hard to produce mechanically complicated things. Only way you get the cost down is mass production. But with serious investments, we could have produced humanoid body years ago. So why are we investing in humanoids right now? The reason lies in the other half of the equation: control. The part that turns the senses into decisions and the motors into coordinated action. It finally has a solution that might actually work. Modern AI can process sight, sound, and motion, and it can do it fast enough to keep the robot upright in a messy world. That's where the renewed interest to design humanoids comes from. And you might ask, why humanoid shape? Well, it's practical. Our tools, stairs, doors, vehicles, they are all scaled for hands, arms, and legs. It's much easier to shape the humanoid to the existing world than to shape the existing world to humanoids. This tour won't cover every nut and trace. This is more of a basic introduction and shows the parts that we'll be talking in the future episodes. Let's start from the head. You might be fooled that there's some thinking going on here. That would be a logical conclusion. After all, brains are usually here, but there's nobody home. It's empty inside. Well, besides the cameras, depth sensors, and microphones, sometimes a display or an indicator light, actuators, and a bunch of other stuff. But the actual brains live in the torso, where they are well protected. Head's purpose is not just to work as a source of input. It also forms an output. It is a common practice to add a display in the face of a humanoid, or at least some indicating light. Humans are wired to read faces, so this is a very natural place to indicating a robot status or communicating some basic intent. Placing sensors where the eyes are have a real benefit. It lines up with our perception. When the robot cameras sit where our eyes would be, it's easy to model behavior directly from the human. Video recorded through people's point of view can be mapped almost one-to-one because the view matches. Symmetry also makes data operation and VR-based training more natural. You see what the robot sees from a familiar angle. So the head pulls double duty, intake of the world through optics and audio, and broadcast of status back out. Not the brains though, but the crucial interface. Citizens, keep this in mind if you end up in a situation where you need to disable one. The neck, on the other hand, sounds trivial. Just aim aforementioned sensors, but it also has additional benefits too. When a robot swivels its head towards something, human instantly rates it as attention. Having a movable head allows for body language that is natural to us. Next, we go towards the torso. Torso works as the main hub. It carries batteries, converters, processors, actuators, and cooling. It absorbs shock, sheds heat, and manages electromagnetic noise. There needs to be enough cooling. That can include things like fans, ducts, heat sinks, vapor chambers, and heat pipes. And all of the main processing and power management is done here also, all crammed into a shell that also supports arms and legs. There are plenty of things going on here. We won't go to all of it now. We will peel into these details in the future episode. If you'd like to hear about these details and keep up with the humanoid progress, I will ring the alarms when we are about to be overpowered with Terminators. You only need to click the bell icon and subscribe. Maybe I should do an episode on all of the T-series robots. Let me know. But from the Skynet to the processing and AI. AI is at the heart of the behavior. It is the piece that turns a pile of actuators and metal into something that moves through the world. Unlike the most large language models that you interact with, like ChatGPT, in a humanoid, the AI model runs locally on a chip. This is to cut down the latency. Other words, make sure that the commands are delivered fast and snappy. The latency that would be caused by the internet connection wouldn't allow the robot to react fast enough. Some reasoning before execution of a complicated task might be offloaded to a cloud, but the actions themselves can't be. But before any of these can be processed in the chip, we need the actual AI model to run. Where do we get these AI models? They are trained. This happens in a massive sprawling computer clusters. They're relatively new, but the very important trick is reinforcement learning. It's a trial and error in a simulated world, where the digital twin falls, stumbles, and retries millions of times. Rewards and penalties shape the behavior, just like ours. Though instead of bruises and tears, the robot earns floating point numbers. The craziest thing about all this, after all that number crunching, all that calculation, all that training, the whole thing collapses into a surprisingly compact file. This file contains what we call weights. These weights are actually small enough to fit in the most thumb drives. Of those who don't remember thumb drives, your phone can hold these weights many times over. You can think these weights as a massive multi-dimensional spreadsheet, and the individual numbers in each cell are called tensors. And a strange and little nerving thing about these multi-dimensional spreadsheets is that we don't really understand how they work. That's right. Not us, and not the people who train them. We don't know how this simple file really causes what feels a lot like intelligent, or in this case, embodied intelligence, understanding of balance, physics, reasoning, action, and control. The tensors are fragments of every little detail of the motion, how to balance, how to grip, how to dance, how to interpret vision. All these fragments need to be put back together in real time. Just because this file is relatively small, don't mean running this model is easy. These chips need to be fast. Memory needs to be big enough to hold the file, and not just any memory, quick memory, and all while sipping as little power from the battery as possible. I bet you haven't heard the word AI lately, but bear with me. If you think about the word AI, it was coined already in the 50s. So why are we talking about it so much now? What suddenly changed? What caused the ChatGPT moment? If you oversimplify it a lot, a branch of AI research that for some quite time had less interest among researchers than the established approach, or more accurately, the approach that yielded more useful results in the past, suddenly had a turning point and very quickly overperformed the old mainstream approach. So that's one of the reasons why word artificial intelligence can trigger different imaginations of capabilities. AI of now is very different from the AI before. I would consider the paper from the 2017, Attention is all you need, one of the key pivotal turning points. Here you can see a simplified timeline of AI progress. As you can see, the breakthroughs are relatively recent and have had massive effects in AI progress. So yes, AI and deep learning has done some massive progress. But why this is so much better than what we were doing before for robotics? Well, before, for decades, the bottleneck was a bespoke code that had to take every tiny variation account. The real shift here is that models can now learn and generalize. Just like large language models don't have to have every answer coded in them. It's the same for robotics. No one needs to hand script every thump, tumble, twist, or a grip. I can't emphasize how important it is that this bottleneck is gone. Believe me when I say it makes all the difference. But enough of that. Even if I could sit here and talk all about AI models and the fascinating progress that have been made. But we need to finish this episode in some point. So let's move on to shoulders and arms. Shoulders do heavy work. They don't just lift their arm itself, but whichever tool or payload it is carrying also. Each shoulder joint packs multiple actuators, and this is a common for all robot joints. You can divide every joint into an axis that determine, does it move up and down? Does it move forward and backwards? Does it rotate? Each axis that the joint moves most likely needs an actuator. Not always. There are different ways to actuate an axis and to have a different amount of actuators. But for now, let's keep things simple. A lot of the human joints are ball and socket, and to try to emulate this roughly, you need to rotate in 3 different directions. That's usually 3 different actuators. And if you multiply this with every joint, you quickly end up with 30 to 60 actuators in total. These actuators are the real muscle of the machine, and usually the hardest part to build well. Most actuators contain a motor and some kind of a reducer. Here is just a few examples of different kind of reducers. Harmonic reducers, cycloidal, planetary gear reducers, screw or other linear type of reducers. And the truth is, almost no choice is perfect. Every actuator design has its compromise, and manufacturers often develop their own variations with their own secret sauce in the house. Manufacturers like Tesla, Figure, Unitree, and Boston Dynamics all devote serious R&D into a custom actuators because even small gain of efficiency, accuracy, cost, or durability translates into huge improvements if you scale it across all the actuators in the robot. One of the key issues is manufacturing. Actuators need to be both high precision and produced in high volume. It's why actuators are such a huge portion of the humanoid total cost, and why companies are racing to find the best solutions. Biceps, elbows, forearms, and the wrist's main duty is to serve the hand. The level of functionality is dependent on what priorities the company has set for the hand. Some have set their aim for human-like arms, while others have more task-oriented vision. If you use actuators located in the hand, the wrist only needs to transmit power, signal, and the movement itself. If you actuated the hand with tendons from the forearm, the game changes. The wrist becomes a very crowded tunnel. Let's investigate why you might want to live with these complications. The hand is a great unsolved problem in robotics. You just need to look at your own hand. Ours is absurdly capable. 27 bones, over 30 muscles, and thousands of sensory receptors packed into a shape that can crush, care, and type with keyboard. It's no wonder engineers struggle to replicate even fraction of this capability. As this is such a hot area of R&D, there's a lot of different approaches taken. Some have opted for tendon-driven hands, where some of the motors are located in the forearm. In this design, cables or similar tendons are actuating the fingers. It is compact and powerful, but it's also complex, and tendons have a bad habit of stretch and wear. There's also another way, fully actuated fingers, which just means that there is tiny motors on each finger. It's clean-looking design, direct control, but as you can imagine, fitting a motor in a finger is very difficult. It can make the hand very heavy, whereas normally not. And most hardest thing is that the relatively small motors have a hard time to fill the power requirements needed. The third option is adaptive or underactuated hands. It's just another way of saying there's no motor for each joint. Sometimes they are clever linkages, sometimes they are tendons that pull multiple joints at the same time. This simplifies the design, but the drawbacks are obvious. You sacrifice some of the motion capability. Soft robotic hand is one option. They can be actuated in many ways, from inflatable bladders to wire linkages. They use compliant materials. They feel slightly more natural. They are gentle and adaptive. They are great on grabbing irregular shapes, but they come with their own unique problems, like precision and manufacturing. The sheer variety of approaches should tell you something. The fact is, nobody has found the perfect solution yet. If one design were obviously best, all designs would just be variation of it. But instead, many labs and companies pursue different approaches. But that's what makes it so interesting. Hands are so fascinating. Unlike elbows and knees, where designs are starting to have some kind of converging, the hands are still totally wild frontier. Some of them manage delicate tasks, some provide strength. Very few of them can achieve both. This area deserves so much more than just this section. In the future, you will get episodes devoted just for humanoid hands. We cover things like tendon routing, tactile, sensing, finger geometry, even the economics of manufacturing such a tiny, high-precision parts. We come to the end of the arm, but not the end of this tour. Next is the waist and hips. The human spine is such a marvel. 33 vertebrae, layered discs, muscles, firing in micro adjustments, hundreds of tons a second. It lets us twist, bend, sway, and still keep a balance, reproducing that in steel and bearings, while currently that's just too difficult. So we are not doing that. Instead, the most humanoid designs cheat. The waist is usually simplified to hinge or two. A joint for leaning forwards and backwards, maybe a joint for twisting, just enough to bend down and reach towards the task, but a very pale shadow of the real thing. It does the work, but it's definitely a simplification. This is one of the places where we admit that the human blueprint is too complex. If this would be totally essential, we would try to achieve it, but we have found out that here lies a place where we can cheat and still get a satisfactory motion. I am sure in the future we'll also improve in this design when we get certain level with everything else. Moving down, the hips, they carry weight, literally and figuratively. They are responsible for bearing the whole torso. Hip joint also helps to manage balance in multiple directions, forward, sideways, and absorbing some of the shock from each step. But the main benefit from a hip lies on how they help initiating each step. Hips are also very important to achieve a natural gait. You might have noticed how weird or stiff some of the humanoids walk. One of the reasons is that they were not using hip to achieve a natural looking walk cycle. Talking about walking, let's go to the thighs and the knees. These are relatively straightforward. They are essentially just big beams that need to be stiff and light. The space is always in premium when you talk about humanoid, but considering how complex everything is, thighs might not be our biggest headache. So let's move on to the knees. Knees are a good place to demonstrate how seemingly a simple joint will have also their own challenges. But if you look closer into knees motion, you realize it has very limited range. But the loads that knee goes through are very varied. When you are standing still, the knee has an easy time supporting you because you're essentially just balancing on top of the joint. But as soon as you do more difficult movement, like raising up from a chair, you realize how much the knee joint and the muscles really need to do. In different angles, knee joint suffers from a very different workloads. This is a perfect place where the traditional mechanical engineering can help out to spread the loads of the actuator, and how different kind of actuating methods can help for different kind of loads. From the knee, we get to the shank. Shank's design is very closely tied to the foot and how it's actuated. Between these two lies the ankle, and the ankle takes a lot of the punishment. Each step causes strain to the ankle. They need to stand twisting stress and shock loads. It's also nearer to the crown, which means need for even better weather sealing. And this brings us to the topic that will be crucial in humanoids. How are they going to last? The challenges of designing something that is low maintenance, it has many moving parts, are major. But I am confident that we can overcome all this difficulty as the industry matures. One of these wear areas are the feet. Most feet are made passive designs. They usually have some compliant mechanism, but very few designs have actuated parts. What they all need is some way to reduce wear and improve grip and protect from the shock. These can be rapid soles, cushioning mechanisms, and sometimes even shoes. I promised you a tour from head to toe, but actually one thing that you very rarely find in a humanoid is a toe, or at least multiple toes. I guess it's just not fashionable with humanoids, or maybe it's telling something about us. Personally, when I look at upcoming technology, I look for the challenges and I try to isolate the ones that we don't know how to approach. If there are any challenges that we don't know how to approach, the technology is still a long way off. But in case of humanoids, I don't see any problems like that. This is why I believe that we'll be seeing humanoids going about the world soon. And these humanoids are not only gonna be out there, but they're gonna get better. I will be analyzing and monitoring humanoid progress, eventually put them to the test at home, garage, and in the garden. I don't know when that day comes, but one thing I know for sure, humanoids won't support this channel. So do your human thing and support another fellow meat sack. Like, subscribe, and leave a real human written comment. See you in the next episode.